Alright, here's my video guide for lesson 10.1.2. Like I said in the last video, everything in this 10.1 is just a further investigation of circles. And so today we're looking at angle measures and arc measures in a little bit different application, and then arc measures and arc length. Just some new concepts that take us a little bit deeper into circles. This is a little bit longer of a lesson because the first problem's a little bit longer, and I really couldn't cut it out because I just really love that problem too much. So bear with me. I think I can be able to do this in two videos. Maybe I just have to move a little bit quicker. And with that said, let's look at the first problem. Okay. This problem, like I said, is one that I really like, and I'm actually even going to read the problem to give it some context to what we're doing here. So Eratosthenes, that's how I'm going to say it, Eratosthenes, who lived in 3rd century BC, was able to determine the circumference of the Earth at a time where most people thought the world was flat. And then that right there makes this an interesting problem, because with the geometry we know, we can do what he did back in 3rd century BC, and we can show that we can find the Earth circumference of the Earth, and people might still believe it's flat. So since he was convinced that the Earth was round, he realized that he could use a shadow to help calculate the length of the Earth's radius. Eratosthenes knew that Alexandria was located about 500 miles north of a town that was closer to the equator called Syene. When the sun was directly overhead at Syene, a meter stick would have no shadow. However, at the same time in Alexandria, a meter stick had a shadow due to the curvature of the Earth. Right there, interesting to me. All right. Since the sun is so far away from the Earth, Eratosthenes assumed that the sun's rays were essentially parallel once they entered the Earth's atmosphere. So that's another important thing. The sun's rays, as they enter the Earth's atmosphere, create these parallel lines. All right. And realized that he could therefore use the stick shadow to help him calculate the lengths of the Earth's radius, and that's what we're going to do here. All right. First thing I'm going to have us notice is that they highlight this part right here. In Alexandria, where the stick is in the ground and we have a shadow, and then there's this angle formed by the sun hitting the stick, the sun's ray hitting the stick, and we're creating this angle that's forming the shadow. And that's what we're going to look at in A here. So unfortunately, the precise data used by Eratosthenes was lost long ago. However, if Eratosthenes used a meter stick for his experiment today, then the stick shadow in Alexandria would have been 127 millimeters long. And so I'm going to actually put that in here. Instead of just saying shadow, I'm going to say that that shadow is really 127 millimeters long. And then it wants us to determine the angle that that ray, we want to determine that angle right there where that ray hits the stick and is creating the shadow. And it says to remember that that meter stick is 1,000 millimeters long. And so the stick is 1,000 millimeters long. And all of a sudden what we have is a right triangle. We know two of the measurements and we want to find the angle. Well, we actually know the trigonometry to do this. Across from that is opposite, and between the 90 and your angle is your adjacent. And so this is a tangent problem, but we're looking for an angle, so it becomes a tangent inverse problem. And so if we want to figure out that angle, what we need to do is, for A, we need to do the tangent inverse of my opposite, which was 127. Opposite was 127, and the adjacent is 1,000. If I calculate that, I'll figure out what my angle is. And I bring out my calculator to do this because I can't do tangent inverse problems without it. And I press the inverse button, then I press tangent, and when I plug it in, I get that that angle is equal to 7.24 degrees. So where the sun hits the stick and goes to form the shadow, that angle is 7.24 degrees. All right, that's just the first step in figuring out Earth's circumference, and a really important step actually, because this next part to me is a little hard to see but very cool. All right, so we assume that those sun rays are essentially parallel. Determine the central angle of the circle if the angle passes through Alexandria and Syene. How could you find your answer? Well, I'm going to try to show you the best I can up here. All right, so these sun rays are parallel, and we have this sun ray traveling in right here, and we have another sun ray passing down right here. Well, this is kind of hard to see, but this angle, what we have here then is two parallel lines, and I'm going to try to use my parallel or my line here to do it. I'm going to actually erase these dots because that's kind of just sloppy. We'll actually use lines to see if this can help me see it. Is we have this parallel line, this sun ray right here, and we have this sun ray right here. And what we have, that's my angle right in there. That's my 7.24 angle. And then actually what we have here is a transversal cutting that. And so that's my angle that I just found from the sun and the meter stick. And down here is the same angle, because that right there are alternate interior angles. And that it helps me figure out what that central angle is. So when it's saying this, how could you determine the central angle? Well, really, because the sun travels in parallel lines, we can use alternate interior angles. And so for B, I'm just going to say alternate interior angles. Alt interior tells me that that central angle is the same as the angle that formed above, and it equals 7.24 degrees. So I think that's interesting, and I actually like the way that I have it drawn up here. Just knowing these sun rays travel in these parallel lines, and we can use that, and then it becomes that geometry of alternate interior angles to say we can find that. I just find that extremely interesting as well. See why I can't cut out this problem? So now we have A and we have B, and it's really nice now because now we've done B and we know this central angle down here, and that's going to help us as we go into C here. So what we have is, since the distance along the Earth's surface from Alexandria to Syene is about 500 miles, so that arc length right there is 500 miles, use this information to approximate the circumference of the Earth. All right? And here what we're actually going to do is we're going to use two proportions, two equal proportions. All right? And what we have is we have 500 miles. We're going to have 500 miles over the total circumference of the Earth. So 500 miles over the entire circumference, but we don't know the entire circumference, and so we just call it x. And then we're going to set that equal to a proportion using our central angle. So we're going to say our small part of our central angle here, our small part of our central angle right there, was 7.24 degrees over the entire central angle, which is 360 degrees. So what I have is I have part over whole set equal to part over whole. And I know those are going to be equal proportions because that 7.24 is related to the 500 and the x is going to be related to the 360, the total. All right. When you have two equal proportions set equal to one another, you are allowed to cross multiply. And so what we can do is x times 7.24 and 500 times 360. And if I do that, I'm going to need my calculator, but I know I get 7.24x from multiplying there. And then 500 times 360 is going to give me 180,000. Exactly. Nice. All right. And then to solve for x, we need to divide both sides by 7.24. And that'll cancel there. And then we get this 180,000 divided by 7.24. And I get an answer that the Earth's circumference, the total circumference of the Earth, is about 24,861.88 miles. So just by using meter sticks in the ground at two different locations and looking at the angle created with the sun, we actually just found out what the Earth's circumference is, which is that 24,861 miles. All right. And now we go into the last part, which is going to answer Eratosthenes' question. And it's going to say, using that circumference, figure out or approximate the length of our Earth's radius. And so what we can do now for part D is we can say, well, our equation for radius, our equation for circumference is 2 times pi times radius. Well, we know that equation, if we're talking about the Earth, we know that that circumference equation needs to equal 24,861.88. Now we're allowed to just solve this for r. What I'm going to do is on both sides, I'm going to divide here by 2 pi, and I'm going to divide over here by 2 pi. 2 pi's will cancel, I'll just be left with radius. And if I do my circumference divided by 2 pi here, I'll have my radius. So 24,861.88 divided by 2 pi, and I want to make sure I do this right, 2 pi all in one, I get an answer of 3,956.89, and that's in miles. All right, and there's the problem. There's the Eratosthenes problem, one that I think is probably one of the most interesting problems, most applicable problems that we do in geometry. Maybe not applicable because we're not going to ever need to do this again, but just an idea like how this could be applicable, how about the things that we've been studying all year long can be applicable and was applicable for somebody to figure out that the Earth was round and that we can actually figure out what that circumference and radius is. All right, again, I used that in the beginning in A, I just used the idea we knew the meter stick and how long the shadow was. That told me my angle. I then used alternate interior angles to find central angle. I then used that central angle and the proportion to figure out the circumference. And then I used circumference to figure out radius. All right. Very interesting problem. If you have questions on it and want to know more about it, please email me. There was also a video that's part of the ebook that does a nice job explaining kind of how that problem is set up. So if you want to, make sure you check that out in the ebook. Let's check out 10-14 quickly. And I don't know, I'll probably be able to get through A, but probably not B, so I'll pick that up in the second video. All right, so this is going to be just looking at different ways that we can talk about angles and arcs. And so here, I'll read this one too, because I think there's just so much important information. In order to find the circumference of the Earth, Eratosthenes used an angle that had its vertex at the center of the circle, so using that central angle. All right, an arc is a part of a circle. We kind of know this already. Every central angle has a corresponding arc. For example, in circle T at the right, the angle STU, so angle STU, that central angle of 40, has a corresponding arc of SU. Since the measure of an angle helps us know it's part of the whole 360 of the circle, an arc can also be measured in degrees. And so I think it says it here. It kind of does in part B, but really what it's saying is we could say that SU, like in the problem above, was 500 miles, or we could just say that SU is 40 degrees of the entire 360 degree circles. It's just two different ways that we can talk about the measure of an arc. We could give it a length, like in feet, in miles, or we could give it an angle measure. And so what it's saying here for part A is to examine the circle above and what is the measure of SU, or you could write it measure of SU arc. What is the measure of SU? What is the measure of SZU? And show how we got our answer. Well, the first part of that, what is the measure of SU? If we're talking about it being written in degrees, it's already given. So in part A, we already have that. If the central angle is 40, and we're talking about doing the measure of the arc in degrees, then if the central angle is 40, then the measure of SU, the arc created by that central angle, is also 40 degrees. And that's the minor arc. All right, I should put that in parentheses that this is the minor arc. And minor arc was a word we learned yesterday. All right, the second part of this question is, what about the measure of SZU, the major arc? So when you're going around the big part, SZU is this major arc. And it's talking about, well, how could we figure that out? Well, if we're talking about degrees, that's a circle and it's out of 360 degrees. And so we can just take away the minor arc and we'll have the major arc. And so if I'm looking for the measure of SZU, that major arc, we do 360 minus 40, and we get our answer of 320 degrees for that major arc. And again, that's just doing arc measurement in terms of degrees. Like I said, I will finish part B and the rest of these problems in the second video.